Good morning, and welcome to this Conservation Applied Research and Development, or CARD webinar. I'm Mary Sue Lobenstein, and I'm the Program Administrator for the Minnesota Department of Commerce Division of Energy Resources on the R&D side. With me today is Mark Garfano, who is an energy engineer at the department, where he performs reviews of custom efficiency projects and leads the department's efforts to maintain and update the Technical Reference Manual, or TRM, that utilities use to calculate the savings and cost effectiveness of their conservation improvement programs. Mark has helped me out today by leading the Q&A section of the webinar, and also as a TRM lead, he'll be able to answer any of your questions related to inclusion of the strategies we'll be discussing today in the TRM. Our topic today is increasing residential boiler efficiency with retrocommissioning and improved installation. Our presenters are Rebecca Olson and Ben Schoenbauer from the Center for Energy and Environment, or CEE. Becky became the Director of Residential Programs when the Neighborhood Energy Connection and CEE merged in 2017. She oversees all aspects of the residential energy programs at CEE, including the Home Energy Squad, the Energy Audit Programs, and the New Construction Energy Consulting Programs. Becky has a deep background in energy program management, energy auditing, and low-income weatherization. In addition, she has served as President and Secretary of the Minnesota Building Performance Association and is the current chair of the Building Performance Institute's Standards Technical Committee. Ben is a senior research engineer at CEE and conducts research on new and innovative technologies and ideas dealing with residential and commercial energy efficiency. His work includes identifying new efficiency opportunities, conducting field research, finding and pursuing funding opportunities, and disseminating the results of the research that he's conducted. Ben's specific areas of focus include water heater performance, service hot water heating, residential HVAC systems, and beneficial electrification. We're very pleased to have both Becky and Ben here for this webinar. Before we start, I want to go over a few webinar basics. First, all attendees will be in listen-only mode. Second, as questions occur to you during the presentation, please type them into the chat box and send them to us so that we can address them later. We will do our best to answer all questions within the time allocated at the end of the presentation, but if for some reason we don't get to all questions, we will answer them later and email all participants a copy of the Q&A from the webinar. This webinar is being recorded and will be available on the department's website at a later date. Finally, the slide deck for this webinar is available on your GoToWebinar panel, where you can download it at any time during the presentation. Just to provide a little context, this webinar is one in an ongoing series designed to summarize results from research projects that are funded by Minnesota's Applied Research Fund, which was established in Next Generation Energy 2007. The purpose of this is to help Minnesota utilities achieve their 1.5 energy savings goal, which awards research grants in a competitive research for proposal process. Results from the CARD project provide utilities with information they need to enhance their energy efficiency program designs within the SIP portfolios. As you can see by this pie chart, CARD projects funded to date have been in all building sectors. The subject of today's webinar is the residential sector, and we'll discuss a project that characterizes existing boiler performance and attempted to determine practical and cost-effective steps to improve performance of high-efficiency boilers through retrocommissioning and also through improved installation. Now I'm going to turn it over to Becky to start today's presentation.
Hi, everyone. Just quickly get this in place. Yeah, there's a little lag on the slides. Hold on one second. There we go. Okay. Hi, everyone. Thanks for attending today. I'm going to talk about the results from our field assessment of residential condensing boilers. As Mary Sue alluded to, the final report for this project will be out shortly and available on the DER and CE websites. So if you're looking for more follow-up information afterwards, that will be available. If you're not familiar with CEE and are interested in learning more, the best place is to go to our website, mncee.org. CEE works on a broad range of topics related to building energy and energy efficiency. We run programs including the Home Energy Squad and one-stop commercial lighting programs. We do planning and consulting. We have a lending department that does financing. We do a lot of policy work, and we have a dedicated research department conducting research related to building energy efficiency. We've done a number of different CARD projects over the last several years, and we'll dive deeper into that one today that Mary Sue mentioned, the quality installation and retrocommissioning of high-efficiency condensing boilers. So the agenda today, we're going to first discuss a little bit of background on hydronic heating systems in Minnesota as it relates to residential buildings. Then we'll go through our field study portion of this project, including a couple phases, as well as some optimization that we did on some of the equipment and the performance results. And then our conclusions about the whole project. Excuse me. So just to give a brief overview of hydronic heating, these are two diagrams of the basics of hydronic heating systems. You basically have a boiler that then that has the combustion process going on. Inside of a heat exchanger, that heat exchanges to water that then gets piped out to emitters or radiators. And there's definitely more simple versions and more complex versions. And you kind of can see two examples of that here on the slide. The diagram in the bottom right shows a system that also includes, in addition to radiators, an in-floor heating loop as well as an indirect water loop, all being powered by the combustion heat of the boiler. A couple things to note is that it's important to understand the difference between a non-condensing or a conventional boiler versus a condensing or more high-efficiency boiler. The key aspect is whether you want those gases to condense or not. So in a conventional boiler, if the gases condense, then you could potentially have some failure issues on the heat exchanger. The heat exchanger isn't built out of materials that can withstand rust, so we really are trying to prevent condensing happening in that system. On the flip side, a condensing boiler is meant to condense, so those heat exchangers are made out of durable materials that can withstand the corrosive qualities of condensate. And in order to get the efficiency of a condensing boiler, we want that to condense as much as possible. The kind of tipping point on where we get condensing or not is really based on the return water temperature. I'll go over a little bit of that in a second, but 130-degree water temperature is really what we need in order to, or that's the tipping point between condensing or not. So if the gases, if the return water temperature is above 130 degrees, then you pretty much prevent condensation. If it's below 130 degrees, that's when you start getting condensation. The radiator types can really play a significant role in this, and that is because the return water is a function of the supply water temperature, and so the more heat that can get delivered to the house through the radiators, the lower the return water temperature can be once it gets back to the boiler. One thing to note is that many condensing boilers are used as replacements for non-condensing boilers, so it's really important to think about these characteristics when putting a different system than the originally designed system for that home is. And so our project mainly looked at, is there any issues with that replacement due to the existing configuration and the emitter type. Here are a couple stats about hydronic heating in Minnesota. Most of the heating systems in Minnesota are forced air systems. However, about 30% are heated by a boiler. Most of these are going to be in the older cities like St. Paul, Minneapolis. However, there's a fair portion in the northern locations of Minnesota where air conditioning is in less demand. Some of the images on this slide, we have in the top right hand corner an image of a condensing boiler. They're often wall mounted. They have PVC venting out the side. Right below that is an image of a conventional boiler. Again, That's typically floor mounted with metal venting to go up and out the roof. On the bottom, we have a few different emitter types. The bottom left-hand corner is kind of the traditional cast iron radiator. In the middle is your fin tube baseboard, and then on the bottom right is an image of an in-floor heating loop. So I'm going to try and illustrate why it's so important for that return water temperature to be low in order to get condensation out of the gases. Because condensing boilers have a secondary heat exchanger that is meant to extract even more heat out of that combustion gas, that is being passed next to the return water temperature. So the lower the return water temperature, the better the heat transfer into that water is. So again, the lowest that we can make that return water temperature, the more likely that we'll have condensation. And that is how it gets its efficiency. So again, the more heat that's extracted out of the gases, the less that goes up the chimney. Excuse me, and that is what helps increase the efficiency. You can't typically set the return water rate. You're typically setting the supply water rate, and so that that supply water temperature set point as well as your emitter capacity is what really dictates that return water temperature. So as we were getting going on starting this project, we were looking at kind of what are the needs that we wanted to find out about residential condensing boilers through our research. And one of the things we noticed was that there was quite a lack of modulating condensing boilers that were in the residential market. So we often see condensing forced air furnaces being put in as replacements in residential homes, but much less so for boilers. So we wanted to look at why that was. There was some anecdotal evidence that HVAC contractors and utilities may have had inconsistent confidence with the performance of the condensing boilers, so some skepticism on their efficiency, and that we thought there might be an opportunity for a quality installation protocol to make sure that we're getting that condensation rate that we just talked about. A little bit more on some of the anecdotal evidence on contractor hesitance and cost. The cost of the condensing unit is generally higher and variable. We would see bids kind of between $6,500 and $15,000 for an installation of a condensing boiler, and we wanted to look at why that range was so large, as well as the top end of that range being so high. There tended to be a lack of confidence in the operation at high efficiency, so how often were these systems condensing was a big question. And then there were definitely some issues with some earlier models of condensing boilers that produced a lot of maintenance callbacks and system failures that a lot of contractors had cited as a concern. There tended to be a little bit of confusion about the supply set temperature and condensation rate, and so we wanted to explore that impact as well. And then we also noticed that there weren't as many model options in the market as their condensing forced air counterparts. We did look at some prior research on condensing boilers. All of these are cited in our final report that will be coming out soon. And generally, they all had similar conclusions. The return water temperature, again, was the primary factor in determining efficiency rates. Flow rates can influence that return water temperature, so how fast the water is moving through the distribution system was a finding from these projects. The outdoor reset control, which really controls the modulation capacity of a boiler, needed to be installed and set up properly in order to get the efficiency. This was a finding from a research project out east. And that we felt we needed a little bit more information pertaining to the Minnesota housing stock and radiator types and climate, and then just some more examples of field performance. So here are a few of the projects that we looked at. This diagram shows that interaction between return water temperature and condensation points. So as you can see, the efficiency steadily increases when the return water temperature is between 240 and approximately 130. And then right at around 130 degrees, the efficiency really spikes up. And so that is the dew point, and that's where you can see this dramatic increase in efficiency. So it's important to try and get below that 130-degree mark in order to effectively utilize the efficiency of these pieces of equipment. However, it's also important to get that return water temperature as low as possible. So as you can see, even below 130 degrees, there's still quite a bit of room for improvement. So this is all to say that that return water temperature being below 130 matters a lot, and we want to try and figure out how we can maximize that while still maintaining comfort within these homes. So a little bit about our project structure. Knowing the questions that we wanted answered, we decided to do a mix of field research as well as market research. We looked at some previously installed condensing boilers to look at how were these installed without any quality installation protocol. What does that baseline look like? And then from that, we wanted to draft a retrocommissioning activity or a quality installation protocol from that. So we tried to optimize those systems and then monitored savings between that as found condition and our optimization condition. Through that, we worked on developing a quality installation protocol, potentially for rebate implementation based on that savings. And then we worked with contractors to install condensing boilers in additional homes using this installation protocol as a way to test out the protocol, make sure that it was user-friendly, and also produce the results that we were looking for. And now we're in the dissemination phase. This is one of our main webinars for this project. So that is, we are almost done. The report will be out fairly soon. So as far as the market research structure, we did mostly in-depth interviews with HVAC contractors as well as homeowners that were participants in the project to get a sense of some of the barriers from the HVAC perspective, what's the pricing, kind of what are the procedures, what are the differences between condensing boiler installation and non-condensing, any of those kinds of items that we looked at that might be market barriers to doing this on a more regular basis. And then we talked to homeowners about their comfort, any issues that they were having with systems as well as maintenance activities. And then we also did some informal interviews with utilities to understand what goes into their rebate development, what kinds of savings were they looking at for condensing boilers, as well as what are the costs associated with those. So here are some results of those interviews. The HVAC companies interviewed, we had 6 companies, one of which was a supplier, the rest were installation contractors. All of them had a fairly low volume of boiler replacements and even lower volume of condensing boilers. There was definitely some hesitation on the cost of the upgrade versus the performance given. A lot of contractors cited that they really wanted to sell something that they valued, and so if they didn't see the value in it, it was tough for them to sell it. And that some of the other conclusions were that the cost seemed to be inconsistent with kind of what we were seeing on the market as far as equipment costs versus labor details. So the interviews with the homeowners about performance, comfort was very high in all of the sites that we talked to residents about. Maintenance did not seem to be an issue with any of the existing sites, and 4 participants stated that they've actually analyzed their bills from non-condensing to condensing, and they were saving on between 10 and 40% depending on the resident. And then all 13 residents that were interviewed did say that they would recommend these systems to others. Some results from the utility interviews. Preliminary discussions did indicate that the utilities weren't very confident with the cost effectiveness, so we wanted to look into that performance and make sure that that information was pretty clear. And that they may, some understanding is that they may be getting high installation cost estimates that go into their calculations, so we wanted to do an analysis on the costs as well. Our field research project setup, as I mentioned, we looked at existing households that already had condensing boilers to study the as-found condition of them. Because we knew we were going to have a fairly small sample, we wanted to make sure that that sample was representative of Minnesota households. So we looked at a broad range of heating loads based on some aggregate consumption data that we had. We wanted to make sure that we had multiple models of equipment as well as multiple installers, so we didn't want the research to be skewed by one contractor doing something. We wanted to make sure that we had households with multiple emitter types, and that there was some representation of indirect water heating, since that was a common replacement option. And then we, based on that prior research, finding that outdoor reset control was so important, we did want to try and find households where the outdoor reset control was missing so we could study that effect. So we did some participant solicitation and selection. We chose 6 sites that had existing condensing boilers installed within the last 5 years. And that all those sites varied in heating loads and construction characteristics, so we did get a pretty good sample of that heating load spread. All of these homes that were selected had cast iron radiators, but several of them had different types as well. So we had some baseboard emitters, we had some in-floor, and we had some of the more modern low-mass radiators as well. And then 3 of those sites had indirect water heaters. And then as far as the monitoring package, we did gas usage analysis, supply and return water temperature rates, flow rates, and then condensation rate, so that we could study all of the performance. So the first half of the 2015-2016 heating season, we monitored those 6 sites without any intervention by us. And then after we had a good set of data for those systems, we made some minor changes to try and optimize efficiency. We adjusted supply water temperature. We optimized that turn down ratio, and Ben will go into a little bit more detail about that. We attempted to change some hot water supply temperatures and flow rates, and then we monitored those adjustments and the performance based on those adjustments. And then we measured the savings between that first section and the second section, and then from that we started to develop some quality installation protocols. So now I will hand it over to Ben.
All right, thanks, Becky. So I'm going to talk through the field characterization results and kind of performance data, and then hand it back over to Becky to kind of talk about cost effectiveness and conclusions and those sorts of things. So what you're seeing now is a slide looking at the instrumentation for our field installs. As Becky mentioned, we really wanted to characterize the energy inputs to the system as well as the energy outputs to the system. And we collected all this data at very high time resolution so we could really look at some of the inner workings and how some of the parameters affected efficiency and performance and capacity and those sorts of things. So phase 1, the as found efficiency results. So the as found condition is sort of how we found the boilers when we walked into the home without any sort of optimization or quality kind of maintenance methods performed. So this is just how they were installed with no sort of specific quality assurance install. And the good news is that they work really well. So we saw across the 6 houses that we monitored, we saw an average space heating efficiency of 90%. These boilers did have AFUE ratings or rated efficiencies kind of 90 to 95%, so maybe we were a little bit below those, but that's pretty typical for field measured efficiencies. Anytime you put something out into actual use, the conditions change a little bit from that ideal lab condition, so you always see a small reduction. So this 90% savings or 90% efficiency number is really quite a good result, and that's right in line with what we'd expect to see, kind of the 12 to 15% energy savings across the board, and we'll talk more about those energy savings as we move forward. But once we saw that these boilers were really working really well, we sort of dug into the data to figure out, well, why are they working quite so well, and why are some of these concerns that people have had about efficiency maybe not seen in these systems, and do we think that, why do we think that's the case? And so there were 3 main reasons for this, and they were kind of surrounding the outdoor reset, the temperature control of the boiler, and the emitters in the house. And so we'll kind of walk through each of those factors. So the first thing, as Becky mentioned, the outdoor reset, we saw some other research that really pointed to this as being a key component of getting boilers to operate well, and we saw some of that too. So for anyone not familiar, in the upper left-hand corner of the screen is a picture of one of the outdoor temperature sensors that can be installed in the exterior of the home and then wired back to the boiler to be controlled. On the right side, you see kind of that control algorithm and how it is changed and set on the boiler itself. And so what the outdoor reset does is it sort of sets the supply water temperature of the boiler, so it also essentially sets the capacity. So hotter water temperatures will deliver more heat to the home. So on your coldest day of the year, you have kind of the highest temperature setting. So this curve shows the kind of factory default of one boiler. So the coldest day for this factory default was set at 0 degrees outdoor air temperature, and at that temperature it had a maximum supply water temperature of 180 degrees. Then as the outdoor air temperature warms, less BTUs are needed by the home to stay hot, and so that supply water temperature can be reduced. In this case, at the factory default, the warmest day was set to 60 degrees outside with a minimum boiler supply water temperature of 100 degrees. And so adjusting these parameters and ensuring that they're reasonable can get you lower and lower supply water temperatures and therefore lower and lower return water temperatures and increased efficiency. So one of the key parameters to the outdoor reset is making sure that you actually know what the outdoor air temperature is. And so it's important to look at what the install requirements are for that sensor. You can see in the lower left-hand corner, this is maybe a non-ideal application of a sensor where you're likely to see some influence from that exhaust that's right next to the sensor. Things you want to make sure in terms of that installation, typically there's some information in the manual, but you want to make sure you're getting a good reading of the outdoor air temperature, thinking about things like exhaust, sunlight, snow accumulation, those sorts of things. The next thing that was really important was sort of an internal boiler control that was key to the performance. And so this is a plot looking at just one site, but it was typical of all the as-found sites and even all the boilers we monitored sort of across the project, is that this is looking at the supply water temperature coming out of the boiler over the time. And so each individual line on here, red, blue, black lines, are a single heating event. So that's a single time your thermostat comes on and calls for heat. And you can see the length of event across the x-axis, in seconds. And so each individual line of that is one time your thermostat comes on because the house needs heat. Boiler turns on, provides heat to the home, and then the thermostat is met and the boiler turns off. So if we look at the different colored lines representing different outdoor air temperature, you can see that, so in the case where it's 30 degrees outside, we have the blue line, there's a call for heat and the boiler kicks on, and the boiler slowly ramps from a starting point of about 60 degrees supply water temperature up to its set point around 125, 130 degrees. But that ramp up takes about 30 minutes to achieve. And so during that whole ramp up time, we're operating at slightly lower supply water temperatures and therefore lower return water temperatures and higher efficiencies. When we move to colder temperatures, say 0 degrees shown in the black line, that ramp up time takes about an hour and a half to reach its set point of about 170 degrees. And so what ends up happening here is that you are sort of increasing the capacity as the event time goes along. And so you're starting your heating cycle at a much more efficient scenario. And so what you can see in the plots is a lot of those red lines, you can start to see that temperature drop dramatically when the cycle ends. So those cycles are ending on average somewhere between 30 and 60 minutes. And so you're a lot of times not actually ever reaching that maximum boiler supply water condition before the house is satisfied. And so you're getting increased efficiency over even what that outdoor reset curve requests. So that was a big benefit and a great control that we saw that really helped reach that 90% efficiency. So then the final big factor that we found was really about the emitters. And so there's a couple of types of emitters, or broad categories, I guess, of emitters that we saw that allowed this good performance. The first kind is sort of these large capacity emitters. And for the most part, that's the old cast iron radiators. And those cast iron radiators are typically very big, but were designed to be used at a high supply water temperature. But thankfully, in all the applications that we saw in all the houses we were in, these cast iron radiators were much larger than they needed to be. So houses over time have improved. We've done small levels of insulation or air sealing. Our boiler efficiency in general has gone a lot up. A lot of these radiators, sort of predate even our 80% efficient boilers, and so they had much less efficient boilers when they were installed. And so all these sorts of things sort of allow, over time, have made these boilers more and more oversized. And so luckily, we were able to, I guess the housing stock in Minnesota allows us to run a lower than designed water temperature through these boilers and still meet the loads of the home. Additionally, any new sort of systems that have been installed tend to be these sort of lower temperature systems. At the top on the right, you can see a radiant panel that's designed for about 140 degree supply water temperature. At the bottom, you can see a radiant in-floor system, and that's designed to be maybe a 95 to 105 degree supply water temperature. And so these newer low temperature systems are sort of set up, designed to work better in condensing systems. So both of those outcomes really highlighted or helped to ensure that 90% efficiency. The one type of emitter we've mentioned that you don't see on this slide is the baseboard, kind of fin tube baseboard emitter, and we didn't see many of those. Where we did, they tended to be towards the large capacity side, and we're able to run a lower than 180 degree water temperature through them. But that there is a potential there, depending on how the systems were designed, for those emitter types to fall outside of these categories. So just something to keep in mind there. The kind of big picture on performance. So here's a plot of kind of each of the sites, the 6 existing sites, and sort of how that return water temperature changed with outdoor air temperature. So all 3 of those factors that we just talked about combined to sort of result in this plot, where you see at colder temperatures, sort of 0 and below, you have higher return water temperatures, in some cases creeping up above that 130 degree mark that Becky mentioned, but in kind of 4 of the 6 sites, never above kind of 120, even at those very cold temperatures. And then as it gets warmer out, you can see that reset curve driving those temperatures down to when you're out by 60 degrees. For the most part, those temperatures are below sort of 100 degrees or so. You can see here that in a few of the sites, about 3 of the sites, at the very cold temperatures, we did need to increase the capacity outside of that condensing range. However, the amount of data there is small enough that those impacts from those handful of non-condensing days were not high enough to bring the total system heating efficiency below 90%. So you can also kind of see, based on that curve that Becky showed earlier, what the approximate efficiencies were at those return water temperatures, sort of ranging from about 94% at 100 degrees up to like 87% efficient at 140 degrees, and then kind of dropping off from there. So those 3 factors really gave us those low return water temperatures that we were targeting, and therefore the high system efficiencies. So despite these high system efficiencies, we still wanted to see if retrocommissioning sort of yielded any improvements. And so you can see the sort of 3 strategies that Becky mentioned earlier that we implied here. And mostly that looks at lowering the total overall supply water temperature, reducing that maximum temperature down, adjusting the reset curve, which included both changing what the coldest day was to kind of adjust the slope of that curve, but also to reducing the temperature set points. And then the third thing we looked at was adjusting some of the DHW interactions. And we'll talk about some of these adjustments with some case studies or some example sites from the retrocommissioning phase. So first looking at that outdoor reset adjustment and supply water temperature adjustment. So Site 7 provided a good example of this. You can see the picture of the boiler and a picture of some of the radiators. In general, we had a good high modulation on this boiler. You can see there the output range sort of between 100,000 BTU per hour and 28,000 BTU per hour. We also did a detailed billing analysis at this house and found that the requirement of the house to keep the house warm at negative 12 degree outdoor air temperature was just shy of 40,000 BTU per hour to keep that house warm. And so then we went through the house and did a pretty detailed characterization of the emitters, and you can see there the range of supplying 180 degrees temperature to all those emitters will give us about 65,000 BTU per hour. If we drop that temperature by 40 degrees, we cut that emitter capacity about in half, but we still give 35,000 BTU per hour, which is pretty close to that design condition for the home. So given that we know what we know about the house and doing those sort of estimates, we kind of walk through the adjustment. So we take that heating load that I mentioned we calculated for this house, we look at that emitter capacity, and then we modify that supply water temperature curve so that it gives us sort of the minimum supply water temperature at the various outdoor air temperatures that will still meet the house's heating load. So that's the process. It sort of requires you do these a heating load analysis, which is, can take some time to do a manual J or to locate the utility bills and do that analysis. You also have to kind of do this room by room capacity, walk around, measure all the emitters, look up in some lookup tables, and do those manual calculations. So this isn't sort of a 5-minute process, but it's also not, a half a day process. But it does take some time. And so we did this at Site 7. What you see here is that supply outdoor reset curve. That the black line that you see on this plot is very similar to that example I walked you through in the manufacturer default, which was what we found when we walked into the home. And then the red line is the curve that we adjusted during our optimization. And each individual point on this curve is a single heating cycle at this home. And so what you can see is that we made a big change in the reset curve, and we got some pretty good reduction in supply water temperatures of some cycles. But what you can see a little bit here is how the intensity of those heating cycles is really in the middle of this plot, and that the change, or the delta T there in supply water temperature, is smaller than it is at the extremes down at negative 20. And so what ends up happening is that this total annual impact is actually not as strong as you might expect. So at this site, we saw about a 1.5 annual space heating improvement, which is a pretty small improvement for the few hours that it took to optimize in the site kind of specific walkthrough that we needed to do in order to achieve that optimization. And so so next we'll look at one of the DHW sites. So very similar to the last site, this is existing site number 3. You can see though in that boiler picture there that we have a 40-gallon water heater, indirect water heater added to this site. And so we looked at how is this water heater performing and what can we do to improve that efficiency. So the first thing we're looking at here is the difference between space heating and DHW heating at this site. And what you can see is that on the space heating side, we're getting those good return water temperatures like we mentioned in the last handful of slides, and we're seeing those kind of 89 to 95% efficiencies on the space heating side. On the DHW side, we're seeing efficiencies in around the 77, 78% range. Much lower than on the space heating side, and that all has to do with that return water temperature and the system sort of optimization. And so we're seeing those low DHW efficiencies. We wanted to look at how can we optimize this, and the first thing we needed to do was assess whether or not there was room for optimization. So we wanted to look at, well, is there enough capacity being delivered currently, and is it over supplying DHW capacity so we have a chance to minimize it? if we have excessive capacity, then we could look at minimizing the supply water temperature or the DHW flow rate in order to optimize that DHW performance. In this case, we did have some extra capacity, and we were able to do some optimization. We could determine that capacity by doing some spot measurements of the temperatures going to and from the water heater, or by doing a reading of the gas meter when the system was in DHW mode only, and could sort of assess the capacity of the system. So we saw that we were a little bit over-delivering on capacity. We're delivering about 60,000 BTU per hour. A standard gas water heater does about 40,000. So we looked at reducing the performance a bit. And the thing you can see on this chart is, in gold is sort of the optimal efficiency. That's essentially a condensing tankless water heater would have that sort of efficiency, where you can see about that 94-95% efficiency. In the orange at the bottom of the slide is what our as-found water heater was doing. And we went through and reduced the flow rates, did some temperature modifications, and you can see we saw some benefit, but not a huge benefit. Here's some of the summaries from some of the flow adjustments. You can see we were able to change the return water temperature some, but not super big changes. We got about 4 or 5 degrees, which resulted in a couple of percent DHW improvement, but nothing drastic. And this has a lot to do with the effectiveness of the heat exchanger in the indirect tank. We recently heard that there's some changing thoughts on how the requirement for a double wall heat exchanger in that indirect tank is changing, and potentially there's some opportunity for some single wall heat exchangers or use of bigger heat exchangers that will allow an improvement of this optimization. But with the equipment we typically see in the field, we're unlikely to yield much improvement. So in conclusion on optimization, yes, efficiency improvements are possible, but the condition of the as-found boilers really made it probably not a cost-effective endeavor. And so in our final report, we provide more detailed steps to doing this optimization. But in general, our takeaway from this and how we developed the quality install guide is really just to get the boiler set up based on the emitter type and following the manufacturer's installs. And that outdoor reset curve, if installed correctly, will really take care of most of the optimization needs in the system. So that being said, we moved on to phase 2, which was new installs. So we were looking to replace non-condensing boilers with brand new boilers using a QI install phase that we developed based on those last protocols, and then monitor that and compare the data backwards. So really the biggest points of this QI protocol are to size the boiler appropriately, ensuring that it does have modulation, which allows the outdoor reset to work and that ramp up control to work. And then the big thing is to get that outdoor reset curve, both the outdoor sensor installed in the right spot and the curve set in meeting this slide shown at the bottom of the screen, which really just optimizes based on the emitter type in the home and is typically found in the manual, but here's a general version if it's not available. Looking at the savings from these new install boilers, they're found in green on this slide compared to the as found in blue and the optimized in gold that we talked about previously. And what you can really see here is that all of these boilers performed at about that 90% level. And based on utility billing analysis and some characterization of 80% boilers that we had, we saw that this was about a 13% savings on the space heating side across all these buildings. On the water heating side, we noted that the power vent that these boilers were performing much like a power vent water heater in terms of efficiency.
All right, now I'm going to quickly go through some of the cost analysis so we have a little bit of time for questions. So we did some additional cost analysis beyond just the participant group for this research project. We looked at about 73 different bids and invoices, 45 of them non-condensing, 38 condensing, and we looked at some of our loan data and some project participation or project participants for installation cost comparison. We compared the average price for non-condensing and condensing boilers, and we did that in two different ways. Right around $2,500 of average difference between non-condensing and condensing installation costs. However, that average was from a range between $550 and $5,000 for the upgrade cost. So that's a pretty large range. And you can see the range for both non-condensing and condensing is both fairly large, but especially for condensing. And then the indirect water heater costs averaged right around $2,800 with a very tight range. I would say anywhere from like $2,700 to about $3,000. So likely would be cheaper if you had an indirect or an integrated tank, as in some of the combi boilers, as well as the single wall tank that Ben was talking about. We just didn't have any in our studies. And as Ben mentioned, there's about 13% savings, or that translates to around $100 a year. So that price difference required for kind of that 25-year lifetime of the boiler simple payback would be around $2,500. So the good news is when we looked at that analysis, the average was right around $2,500. That will vary, of course, based on the contractor and the equipment. But if we wanted to push that price difference to be more of a 10-year payback, make it a little more attractive to customers, we'd really want that to be around $1,000 of price difference. And when we did some analysis on the actual equipment cost, it looked like the average difference between non-condensing and condensing was about $1,000. And so the conclusion is that, yes, it's cost effective. There's likely some improvement to be made on that payback. So a few conclusions on this project is that even the boilers that did not have the aggressive reset curves were efficient because of those things that Ben mentioned. There's about 1 to 3% savings potential if you went through that intensive setup procedure that will be outlined in more detail with our report. And that process is likely not very cost effective to go through, but definitely something to look at. We did not see any evidence of early degradation of systems. We looked at systems that were as old as 5 years, and we didn't see any signs of that even with customers that did no maintenance. So that was something we heard from contractors as a concern, and we did not see any evidence of that. Customer satisfaction was very high. That was really interesting to learn from us, from this project. And that, again, emitter capacity in the homes that we studied and typical Minnesota homes was very high, and so that tends to be not a concern that we saw. As far as DHW integration, DHW performance for indirect water heaters definitely aligned more closely with power vented water heaters than condensing version, and we didn't think they were quite cost effective unless they were cost competitive with power vented. So that cost would have to come down probably around $1,000 in order to be competitive. Likely the integrated tanks and potentially the single wall ones might be a little bit more cost competitive. So in order to become more cost effective, we really feel like there's room for the difference between non-condensing and condensing to come down. Shooting for that $1,000 mark would be kind of the place to be. In our interviews with HVAC contractors, we did not find a significant difference between the typical installation of non-condensing and typical installation of condensing, such that there would need to be an increase in labor costs, maybe a slight, but should likely be able to be around $1,000 total. And that really what's important is the comfort and confidence by the installation contractor to make sure that that price is competitive. All right, we rushed through that. Now we have a tiny bit of time for questions.
Yeah, thanks. Thanks, Becky and Penn. That was a great overview of the research results. If you have not already done so, please send us your questions via the chat box in the GoToWebinar panel so we can answer them. Now I'm going to turn it over to Mark, who's been monitoring the questions as they've come in. And probably we're going to go over about 5 minutes, I guess, on this webinar, and I hope you can stick with us. Mark, do you have questions for Becky or Ben?
Yes, I do. And first, I want to thank Becky and Ben for the presentation and all the information they provided. It's a really interesting topic. So the first question I have, has there been any analysis regarding the performance and cost effectiveness of outdoor reset controls as an option on a non-condensing boiler?
I think outdoor reset controls are typically used on just condensing boilers. The issue with using one on a non-condensing boiler and in general increasing the efficiency of non-condensing boilers is, as Becky mentioned, if you get too much condensate buildup inside of a non-condensing boiler, you risk damaging the heat exchanger and burner and other internal components, and can really impact the durability of the system. So typically people with non-condensing boilers want to stay away from the condensing range. Okay.
Next question. It says, Ben, from your simple instrumentation diagram, it appears you measured your measurement system accounted for a primary-secondary pipe system. Do you have any comments on the ability to get to the highest efficiency from either a primary only or a primary versus secondary pipe system?
Yeah, that's a level of detail, I guess, that we didn't get into, but an important one. That primary-secondary loop plumbing configuration is basically the standard configuration for condensing boilers. And they do that in order to control the flow rate within the boiler itself. The big, excuse me, for boilers, the big thing is really to just ensure that the boiler is set up to work well so that you know what the return water temperature is going into the boiler. And so that really has to do with matching flow rates in those two loops. In general, the boiler manufacturers have sort of optimized that control, so we didn't see it as a big problem in these installs. Speaking from some past research where we were trying to do some different things with different types of emitters and zones, if you go outside of the typical design parameters for these boilers, then you start getting into issues with primary and secondary loops. But for hydronic applications, the pumps internal to the boiler and in the distribution system work well together.
Okay. Next question I have is, what makes and models of condensing boilers were included in the study, and what makes models of indirect water heaters were studied?
Can you say that again, Mark? We missed a little bit of that.
They were wondering what makes and models of condensing boilers and indirect water heaters were included in the study.
Great.
We kind of picked those based on our site selection criteria, which mostly dealt with the home characteristics and then just getting a diversity of models and installers. And I guess in general what we saw was that there wasn't anything for us to say one model or manufacturer is different or better than another. We didn't specifically try to look at that, but we did try to get a range and didn't see any big differences or both in terms of performance but also in kind of operation. So
yeah, and we did set our targets for participant homes to have mostly the most common condensing boilers. So we got some rebate data from Centerpoint Excel and Merck to see what are their most common condensing boiler rebate applications. And so we wanted to make sure that we weren't getting really obscure products. So they generally fell into this, top 3 or 4 manufacturers. But we did get a variety. I think we had, 5 to 7 different models and makes.
And those will be in the final report, yeah. The specific information.
Okay, thank you. Next question, how often would you recommend a steam trap study for residential systems?
We didn't specifically look at that. So I guess my recommendation would be to just look at manufacturer requirements.
Okay. Next question. Since you had a fairly small sample of HVAC contractors that you interviewed, how did you identify which contractors to include in the sample, And do you feel as though it was a fairly representative sample?
That's a good question. We were originally looking for a wide range of contractors' I guess, thoughts and attitudes towards installing condensing boilers. So we really wanted to get contractors that were really pro, they push it every time, all the way to people that never want to install them. So we did some pretty blanketed outreach, lots of contractors that had participated in rebates or any of our loan programs, as well as working through suppliers and distributors to see what contractors did a high volume of boiler retrofits. However, I would say that we got mostly in the middle. So we did not get anybody who adamantly opposes them, and I don't think we really got anybody who on every case drives the sales of them. So we really got kind of that middle representation, which gives us some insight about what are some of the hesitations versus some of the upsides that the contractors mentioned. We also did interview a supplier that tried to aggregate some of the concerns and comments that they had heard from some of their customers. So that was the way that we could try and get a little bit of a broader perspective.
Okay, thank you. Next question. I've heard that regular maintenance and cleaning of the water side of the domestic hot water heat exchanger is important to prevent the buildup of calcium and other hard water minerals that could affect the efficiency. Did you look at this at all when you were looking at the degradation of the efficiency of the boiler installations that had domestic hot water loops and had been in for 5 years? Even if you didn't look at this, do you have anything to say about that issue in this type of system?
Yeah, it's a good question, and we've heard that as well. Looking at these indirect boilers, in this study and a previous study that we did, I've been able to look at a handful of these different systems. So our sample size isn't huge, but it's something like 10 sort of indirect or DHW provided by boiler systems. That kind of range from a brand new to 5 years, 7 years old. And they all sort of perform similarly to the plot that I showed for the example site. Nothing that really indicates that there's significant reduction in performance, but given that there's only sort of a 7-ish year time span, maybe something isn't showing up, or there might be durability concerns. So we didn't look specifically at that, but we don't see a ton of evidence that there's a lot of degradation going on in these systems.
Okay. Another question. In the phase 1 site example cited, it appears that the boiler is quite oversized, a design load of 38,500 BTU per hour versus 99K. What effect do you think can be attributed to oversizing, since most of the year the load is, of course, way lower than the design load? It appears the penalty is not very great given the measured efficiencies.
Yeah, it is definitely, for the most part, the boilers were oversized. I think part of that is due to the fact that there aren't a ton of really small boiler equipment. But the other part of it is just due to, I guess, inefficiencies in the design load calculation and just kind of replacing one size boiler with the same size boiler that's already there. In terms of performance, I do think, and we maybe didn't emphasize it as much on our QI guide as we should have, I do think it's important to remember that most of these boilers have a pretty high turndown rate. So even at that site that was way oversized, the minimum efficiency was still like 10,000, or sorry, the minimum capacity of that boiler was still about 10,000 BTU per hour below the design load. And so it did still have some room to modulate down below design load at the home. And so that was good to ensure that it wasn't always oversized or always operating at much higher design capacities than is needed. In general, I guess we didn't see cycles that were so short that it was really having a huge impact on efficiency, but there are definitely some impacts of that oversizing. It would obviously be better to have a boiler that had a maximum capacity of something like 50,000 BTU and modulated down to 5 or something. But we didn't see a huge impact from that due to the modulation that was present in the boilers.
Yeah, so like Ben said, I think the key is to size it. Use a fairly accurate sizing model. Model J is obviously recommended, or Manual J is obviously recommended, and then within that to pick kind of that lowest minimum firing rate, so a high turn down ratio, and that really made more of a difference than the high side of that.
Another question, did you get any data on the comfort of a system with a condensing boiler versus the comfort of the hotter water in a non-condensing system?
Yeah, that was a main part of our survey interview questions with the participants. Not all of the participants had experience with a non-condensing before the condensing, because a lot of them had either moved into that home after the condensing system was already in or had very little time between them. But of the customers that did have experience with both, they all rated the comfort as the same. And so that didn't seem to be an issue at all. And like Ben said, even when we optimized these systems, we did some pretty detailed calculations to ensure that we weren't going below that comfort threshold. But we also kept that line of communication open with participants in case they were experiencing, colder rooms or anything like that. We had no feedback from that. So no, we didn't have any evidence to suggest that there was any comfort sacrifice.
And one last question. What are your thoughts about addressing the large variation in upgrade costs between contractors? For example, do you think it is a matter of more general education to reassure contractors regarding the variability of condensing boilers in the residential market? Or do you think more specific training is needed to give contractors more experience and confidence about installing them? Or do you think it's something else?
I think that's a good question. One of the answers to our survey questions to contractors that I found very interesting was that one of the contractors had mentioned that they are building a customer relationship every time that they're in a home, and so that it was very important to this salesman that if he was pitching something, he wanted to feel confident that that efficiency upgrade was really worth it. So I'm hoping that, with these results showing that they're even on the most basic non-intentional installation, that these are still operating probably better than expected, that hopefully that will, getting this information out there will help contractors have confidence that if they're selling something more expensive, that it could be worth it. And then I would say just based, again, on the contractor interviews, still kind of a lack of confidence in some of those maintenance issues that were more evident in the early models of condensing equipment, kind of 20, 25 years ago. But that contractors that did a higher percentage of condensing boiler replacements hadn't had that in a long time. And so really dialing into a product that you feel comfortable with on that maintenance and failure issues is really important. And then I would say just doing them more, really getting a sense of what it takes to get those installed and not worry too much about any sort of specialized details. So I'm hoping that, the dissemination of this information will help. I think that working with product reps to really discuss some of these issues that contractors have or concerns that they've had to try and make that evident. But we're obviously open for suggestions too. From this project, we really saw that there's definitely some opportunity to reduce that upgrade cost, and we'd like to see the condensing boiler market similar to the forced air condensing market and really have that cost shrink as much as possible. Any thoughts, Ben? Okay.
Good to go.
Now turn this back over to Mary Sue to close this webinar.
Great. Thanks, Mark, and thanks, Becky and Ben. If you have follow-up questions about this research, I'm sure that Becky and Ben would be happy to hear from you with your questions. So just to let you know again that the recording of this webinar and the final report will be available on the Department's Applied Research and Development webpage at a later date. When it is available, you can either link to either of them from the webinar quick link or from the card search quick link as indicated on this slide. And This R&D webpage has some other information that you might want to check out. The address is at the bottom of this page. So thanks again for participating. We really appreciate your interest in the results of CARD projects. Before we leave, I want to take this opportunity to mention another upcoming CARD webinar on April 25th. Seventh Wave will be here to provide a holistic look at energy savings in the small commercial sector in Minnesota and to recommend strategies for increased participation in energy efficiency programs. Announcements about upcoming webinars and other news related to the Minnesota SIP program can be found on our SIP newsletter. You can link to this newsletter to sign up for it on the slide here. There's a link. Then in the meantime, contact me if you want more information on this upcoming webinar, or if you have questions or feedback or suggestions for the CARD program. So thanks again and have a great day.